study of Laplace transforms. So we'll continue where we left off, which is essentially before I continue from where I left off, one small correction from my previous lecture. I had, as usual, made a small sign mistake. You see, sine 80 into cos bt is equal to half sine a plus b times t plus sine of a minus bt. But I had written this as minus, and that is why I was stuck with one of the problems where I know the answer must be something plus, and then I was getting minus. I'll show you. So this is the correction. Please, yeah, I know. You have to be careful. I had to be more careful. You please be careful in your examination. Sine 80 into cos bt is half sine of a plus b times t plus sine of a minus bt. But previously I had written this minus, so that's wrong. That was the mistake. So because of that, in this particular case, I had written a plus here, whereas actually it should be a minus. Of course, minus and things like that will become plus, and rest of whatever I have told is correct. Final answer was correct, just that I had missed the minus here, so I was wondering what happened. So I went back and saw the formula which I had shown was wrong. This is the correct formula. So please make this correction. Okay. So now let me get on to where we had stopped. That is just 1 minute. I want this. Okay. So this is what we have been studying. So let me briefly recall whatever we had done. So we had defined Laplace transforms, found Laplace transforms of some very elementary functions, used linearity property of that, made a table of Laplace transforms of some standard functions, found out that Laplace transform is linear, used that to find Laplace transform of some slightly more complicated than the elementary functions like sine square t, cos x square, or e power 3t minus sine 5t, things like that, or even cos cube at, and things like that we have done. Okay, so that is one level, and that's basically uses linearity and somehow well you know your old trigonometry and how you integrate and things like that. Then after that, we observed certain properties of Laplace transform. So these were the properties of Laplace transform which we saw. That is change of scale property, which is L of f of at is 1 by a capital F of s by a. So what is capital F? Again, let me emphasize. Laplace transform of small ft is capital F of s. This is a standard notation, and I'll keep using this and recalling this all through this set of lectures. Then the very important property of change of frequency or shifting rule. That's essentially said, if you know Laplace of small ft, then you know Laplace of e power at into ft. All you have to do is shift s by s minus a. That's how it's called shifting rule. So it has engineering meaning also, but I will not bother about that right now. So what this formula says is, let me recall, Laplace of e power at ft is capital F s minus a means if I know Laplace of small ft, then I know Laplace of e power at into ft. All I have to do is to change in s, I have to change s minus to I have to change s to s minus a. That's all I have to do. There is no other, purely an algebraic operation. Just replace s by s minus a, as simple as that. It looks very innocuous, but it's very powerful. And then another result we saw is what happens to Laplace of a function when I multiply the function by t power n. So that again the formula is Laplace of t power n ft is minus 1 power n nth derivative of capital F of x, where capital F of x is Laplace of ft. So this again says, if I know Laplace of ft, I know Laplace of t power n ft. No means I have to do very elementary work, just differentiate it n times. This is particularly useful, and we will use it many times when n equal to 1, which is Laplace of tft. So Laplace of ft, I know. How do I find Laplace of t ft? Just differentiate Laplace of ft by once and then change the sign. That's what it says. So Laplace of t of t is minus d by ds of capital F of x. And I emphasize this, I'll repeat it again. This multiplication by t corresponds to differentiation. So integration corresponds to division by t. Some sort of, like at some level, some interesting masala is happening. We won't go into details of that, but just keep it in mind. So here L of ft by t is integral of capital F of s ds. That means if I know Laplace of small ft, I know Laplace of ft by t. All I have to do is whatever I know Laplace of small ft, I integrate it. In this case, if I know Laplace of ft, I want to find Laplace of t ft, we just differentiate. So by differentiating and integrating, I do some algebraic operations. That's what is the connection between the solving differential equations using Laplace transform, which means I transform the given differential equation to an algebraic one. We'll do this in the later part of the course, but first understand these steps. So these are the formula. These are proofs are very easy. It's not difficult, but it's not there in the syllabus. So I will not go into details of the proof. But I very highly recommend that you try working it out. Just follows from the definition. At the most, you have to use some differentiation in your integral sign, which you have learned sometime. But even that is very rare. We need to know basic differentiation integration, do it correctly. That's about it. So these four, using these four, we will try to find Laplace of more complicated functions. So here it is. These are the illustrations. We saw this already. Laplace of e power 2t sine 4t. How do I do that? So I know this function is of the form e power at ft, and I know Laplace of ft. So I know Laplace of e power at into sine ft by using shifting formula, which says in that Laplace of ft, you just replace t by replace s by s minus a. In this case, s minus a is 2, so s minus 2. So this we have seen it, so I am going to same thing here. Laplace of e power 40 t power 5. So here again I'll find Laplace of t power 5. That's easy, I know that. But this is of the form e power at ft. So I find Laplace of t power 5, which is 5 factorial divided by s power 6. And now I throw out s and replace it by s minus a, which is 4, so it will be s minus 4. That's about it. It's as simple and straightforward as that. And then we are trying this. I think we have finished this also, so let me quickly go through this. Laplace of e power minus 3t cos square phi t. So same thing. This is of the form e power at ft, where ft is cos square phi t. But basically that means I need to find Laplace of cos square phi t. If I find that, then s in that should be replaced by s plus 3. That's what we want to do, correct? So you use shifting formula, you get this. So, but how do I find Laplace of cos square phi t? We already seen Laplace of sine square something how to do. That time I told you how to find Laplace of cos square. So we basically use cos 2a is equal to 2 cos square a minus 1. So in this case it turns out to be this cos square phi t is cos 10t plus 1 by 2. And then no, Laplace of cos square phi t is half Laplace of cos 10t plus L of 1, which I know how to find this. And then replace, if I want to find Laplace of e power minus 3t into cos square phi t, I just replace s by s plus 3. There we go. So that's Laplace of e power minus 3t cos square phi t. Now I think this is what we are doing. I don't remember, but anyway, I'll tell you this. Laplace of t cos 60. So similar, we already use those formula basically. So Laplace of t cos 60 means if I know Laplace of cos 60, I can find Laplace of t cos 60. All I have to do is differentiate it once and change the sign. Differentiate it means what is it? Laplace of ft. So this is the formula which I am using. Laplace of t ft is minus d by ds Laplace of ft. Here ft is cos 60. So factor f of s is s by s squared plus 36. I hope I do these things correctly. If I make a mistake, you should correct this, because I don't remember whether it is 1 by s squared plus 36 or s by s squared plus 36. First things you have to refer to table of Laplace transforms. I hope I have done it correctly, but in case I made a mistake, please correct it. But what I am trying to tell you is what is the idea behind finding Laplace of t times some function. So if I know Laplace of the function, I know Laplace of t times the function. All I have to do is differentiate this once. This means differentiate Laplace of the function once and change the sign. That's what I'm doing here. So Laplace of t cos t is minus d by ds of x by x square plus 36. Now to do that, it's an easier quotient to denominator square into derivative of the numerator. Derivative of the numerator into denominator minus numerator into derivative of the denominator. So I've done that here and I get this answer. I don't trust me. The final answer is correct. Mostly it will be correct, but it could be wrong. So please check because I could have made mistakes with plus and minus and squares and cubes and whatever. So please check these things on your own. I think this is what we will do. Laplace of t is e power minus 2t sine phi t. How do I do this? You see, if the problem would have been easy if instead of giving 2, if they had given me only 1. Here there are t also is there, e power minus 2t also is there, sine phi t is also there. 3 of them are there. If only 2 of them are there, it would have been very easy. If for example, Laplace of e power minus 2t into sine phi t is very easy to find. All you have to do is find Laplace of sine phi t and in that replace s by s plus 2. If I had been given only t into sine phi t, that also I know how to do. I'll just find Laplace of sine phi t and differentiate to find Laplace of t times sine phi t. All I would do is to differentiate it once and change the sign. That's what I will do. So now they are given both. Do both, one after the other. What should I do first, t or e power minus 2t? I will do t first. Why? Because if I know Laplace of t sine phi t, it's very easy to find Laplace of e power minus 2t into t sine phi t. All I have to do is replace s by s plus 2. But if I know Laplace of e power minus 2t sine phi t, to find Laplace of t into e power minus 2t sine phi t, I have to differentiate it once. Differentiation is always a bit more painful compared to replacing s by s plus or s minus a. So I will first differentiate off when the expression is simpler. Differentiate it and then afterwards replace. That's the algorithm. You do it the other way also, it's correct. It's the same thing you get. So let me write down the details. So this given function is of the form e power at t ft. See, I cleverly changed t and e power at because I know I want to, if I can find Laplace of this, finding Laplace of this is easy. But if I find Laplace of this, and then finding Laplace of t into that is a bit more work. It's correct, you can do it that way also, but this is easier. So this is what I will do. So Laplace of, first I will find Laplace of t sine phi t using this, and then I will find Laplace of e power minus 2t t sine phi t using this. So how do I want to do that? Here are the details. So if I want to find Laplace of t e power minus 2t sine phi t, first I will observe that I know Laplace of sine phi t is 5 by s square plus 5 square. And now because of which Laplace of t sine phi t is just differentiate this once with respect to s. That's easily done. Differentiate with respect to s using quotient rule. Numerator is a constant here, so there is no issue at all. So, or you use chain rule directly, which is the same thing. So I get denominator s square plus 25 whole square, and numerator is minus 5. Actually 5 into derivative of denominator, but there is a minus outside. So sorry, minus is always there. So minus of minus, so it will become plus 10s. Yeah, it's all right. I need to spend time on this. D by d minus of d by ds of 5 by s square plus 25 is denominator square s square plus 25. In numerator, I'll get denominator into derivative of numerator, which is 0. So I won't write that. Minus numerator into derivative of denominator, which are written as 2s5 minus 5 into 2s. That's minus 10s, but there's one minus outside, it becomes 10s. So I think I've done it correctly. So 10s by s square plus 25 whole square. That is Laplace of t sine phi t. But that's not where my problems end. My problem says find Laplace of e power minus 2t t sine phi t. So then that I know how to do. If I know Laplace of t sine phi t, I know Laplace of e power minus 2t t sine phi t. All I have to do is replace s by s plus 2, s minus minus 2, which is s plus 2, which is what you see on your screen. So that is 10 s plus 2 divided by s plus 2 whole square plus 25. So these are standard tricks. These, like, you play around with t and e power t. Of course, if I don't like you, I can do, instead of t, I can do t square also. Differentiate twice, or can you do something else? They are all the things which I leave to you figure out. So here is, what figure out. Here there's already a problem based on that. So here I'm asking, find Laplace transform of e power 8 e power minus 5t sine hyperbolic. Pretty bad. Here you see I can do several things, of course, but let me start. First approach, first thing which I want to try is this. If I know Laplace of sine h2t, then I can find Laplace of maybe e power minus 5t into sinus t. Yes, I know I'm to replace x by s plus 5. But then e power 8 into that, I have to differentiate it 8 times. That's a bad one. Even in my first PC, I did not do it. So now I'm not going to do that. So multiplying, if the power is reasonably high, it's not worth using that formula. There must be some other way of doing it. It is possible to do it that way. Please understand what I'm saying. If I moment I see this problem, it's clear that I know Laplace of sine hyperbolic 2t. Then I know Laplace of e power minus 5t into sine hyperbolic t. Then if I want to find t power 8 into e power minus 5t into sine 2h, sine h2t, I have to differentiate 8 times. Differentiating 8 times is not something which is welcome, or not something which is enticing. So I want to avoid that. How do I avoid that? So let us see it more carefully. So can I write it in some other order? In any order I write, whenever I write t power 8, I have to differentiate 8 times, which is a painful thing. So how about attacking t power 8 itself directly? But then how am I going to find out sine h2t into something? Its Laplace transform. Yeah, then you have to use the definition of sin h2t. Remember, these hyperbolic functions are, most often, more often than not, it's easier to use its definition directly and solve it. That will what will give you, because sin h2t is just a notation for e power 2t minus e power minus 2t by 2. It's just a notation. So it doesn't have any other special property. I mean, it has a lot of nice special properties, but you don't have to, you don't get any computational advantage if you use directly sin h2t, except that you will write a bit less, but work is the same. So this is a general theory, general philosophy. Don't bother too much about properties of hyperbolic sine 2t. Just use the definition and go ahead. So I'll show you how I have done it here. So t power 8 e power minus 5t is hyperbolic sine 2t is nothing but t power 8 into e power minus 5t into definition of sine hyperbolic 2t, which is e power 2t minus e power minus 2t by 2. So let's expand this. So this is nothing but half e power 8 e power minus 3t. Please note here. So this e power minus 5t and e power 2t will become e power minus 3t. And the same e power minus 5t and this e power minus 2 will become e power minus 7t. So this, I should be able to find Laplace of this without differentiating 8 times. All I have to do is find Laplace of t power 8 and then think of this function as of a form e power 80 into ft. Here it's written in terms of e power 8 into e power minus 3t, but think of it as if it is e power 80 into ft. So take ft to be t power 8. Same here also. Ft is t power 8, but e power 80a is different here. Here it is minus 3, here it is minus 7. So if you use that, it's over. So now Laplace of t power 8 is 8 factorial by s power 9. So that means Laplace of this given whatever function I have to find, t power 8 e power minus 5t sine hyperbolic 2t is same as Laplace of this, which is Laplace. I use linearity of Laplace and pull out half. So I'll get a Laplace of t power 8 into e power minus 2t minus half Laplace of t power 8 into e power minus 7t. But then this is nothing but in Laplace of t power 8, I have to replace s by s plus 3. And for this, in the same Laplace of t power 8, I have to replace s by s plus 7. I hope it's clear. Nothing much here. All I have to do is use definition of hyperbolic sine. I told you this. Hyperbolic sine is just a notation for some other standard function. So if you try to look look for some formula or try to look for that Laplace of sine hyperbolic won't help you much. May help sometimes, but mostly it won't help because you directly take sine h 2t is e power 2t minus e power minus 2t. Then you will get the solution much faster. So as you can see in this, it turns out to be correct. And then remember, how did I realize I had to do this? That is important for me. You have to understand that t power 8, it is tempting to use that third formula. Laplace of t power n into ft is minus 1 power n, nth derivative of f of s. Nth derivative means, I have to differentiate 8 times here because I'm multiplying by t power 8. That should be the clue for you. Don't ever, I mean, nobody, how much ever people don't like you, they will never ask you to differentiate something 8 times. So that is not something which you would want to do. So avoid that. How do I avoid that? First, find the Laplace transform of that. That is what we have done in this case, in this example. I hope it is clear. This is a general philosophy, as I said. Now let us, there is another formula where we use a Laplace transform of some function by t what happens. So let me illustrate a couple of problems based on this formula and then we are sort of in a good shape. So I want to find here Laplace transform of sine 60 by t. So we'll use the same, there's an obvious formula to use. Laplace of ft by t is integral of Laplace of ft in small ft, which is capital F of s, with respect to s. So how do I do that? So I have to first find Laplace of ft. ft is here 60, sine 60. So Laplace of sine 60 is 6 by s square plus 6 square. So Laplace of sine 60 by t is integral of 6 by s square plus 6 square ds, which is, this is a standard integration you must have done in your class 12. You must have done differentiation chapter, you must have learned it somewhere. Integral of a by x square plus a square dx is tan inverse x by a. How to recall this? See what is the derivative of tan of x by a. Derivative of tan of x by a is a divided by x square plus a square. These are all things which you should know well. Otherwise, you won't be able to attempt these problems, especially integration. It gets worse. So you have to know these standard integrals. So if you don't know, go home, open out your class 12 textbook. There is a table of integration. Use that. If you don't have your class 12 book, use internet. Use the standard. I have shared already some web pages that Lamar University, Paul's online notes. It has all sorts of these kind of formula and then how to solve these problems are all there. Please go through that once. To recall all these formula before your exams, you will read this because this is the crucial point. Otherwise, this formula is easy. What I'm trying to tell you is what you are being taught, what you are being taught in third semester B is easy. That is easy provided you have understood and you can do your proficient with what you have already been taught in your first PUC, second PUC, and first year B. Otherwise, it won't be possible. So that is what this is. And now this tan inverse of s by s6, this limit is between s to infinity. Just one sec. So this limit is between s equal to limit is from s to infinity. So then if I put infinity, tan inverse infinity becomes pi by 2 minus tan inverse pi s by 6. If you want, you can write it as cot inverse s by 6. It's okay if you can do it, otherwise it doesn't matter. Leave it. So I hope you understood how to solve this problem. This is Laplace transform of sine 60 by t. How do I do this? So I use this formula. Laplace of ft by t is integral of f of s. So basic thing you need to know is integrating this year class 12 integration. Otherwise, these problems sound very tough and you're completely lost. And now let us see one more horrendous creature like this. So this is e power minus 5t minus e power minus 60 by t. First attempt could be, let me try e power minus 5t by t minus e power minus 60 by t. But it won't help you much because anyway you have to integrate twice. But integration twice, not integration, integrate twice. You have to integrate. First, you will have to integrate Laplace of e power minus 5t, and then you have to integrate Laplace of e power minus 6t and take um, difference of the two, both from s to infinity. So one can do it, but I'll try to do it in a slightly different way, which is I'll put the both of them together, which is Laplace of e power minus 5t minus e power minus 6t by t is by that formula Laplace of e power minus 5t minus e power minus 6t integral of this from s to infinity. This is the formula. Laplace of ft by t is integral of Laplace of f with respect to s and limits varying from s to infinity. So I am using that. This I know. I know Laplace of e power minus 5t minus Laplace of e power minus 6t. I know this is nothing but 1 by s plus 5 minus 1 by s plus 6. This I know how to integrate. 1 by s plus 5. What is the integral of that? Log of s plus 5, correct. So this is log of s plus 5 minus log of s plus 6, which is shortened into saying log of s plus 5 by s plus 6, and ranging from 0 s to infinity. Please recall all these limits, they are all important. So Laplace of e power minus 5t minus e power minus 6t by t is log of s plus 5 by s plus 6, limit of s from s to infinity. Now let's try to evaluate it. This is what I told you. There will be some problems when you are trying to evaluate these limits. Uh, if I put s equal to infinity, I'll get infinity by infinity. Infinity by infinity is not even defined. So log of that goes for a 6. So how do I do this? You must recall this from your first PUC. You must have done problems like this. They must have asked you a problem like find limit of logarithm of s plus 5 by s plus 6 when s tends to infinity. Limit of s tending to infinity. How do you do this? Can you recall? Easy. You basically divide both numerator and denominator by s, because then I'll get 5 by s and 6 by s, which will become s tends to infinity. They become 0, and instead I'll have 1. So that's precisely what I'm doing here. Okay, doing that in two parts. So first, log of s plus 5 by s plus 6 from s to infinity means I will write this. First, I will not substitute s equal to infinity, I'll write it. Limit of log of s plus 5 by s plus 6 s tending to infinity minus limit of s plus 5 by s plus 6. I just put the limits, that's all. I mean, I'm not put the limits, but I'm trying to put the limits. The upper limit is infinity, which I'll write it as limit s tending to infinity. Lower limit is s, so I substituted value of s here. So this is limit of log of s plus 5 by s plus 6 as s tends to infinity minus log of s plus 5 by s plus 6. How do I evaluate this? This is what I told you. You divide the numerator and denominator by s and you're in a good shape. So moment you do that, you will get 1 plus 5 by s and 1 plus 6 by s. You divide both numerator and denominator by s. I can do that because s is tending to infinity, so I'm equal to infinity. And now as s tends to infinity, 5 by s tends to 0 and 6 by s tends to 0. So 1 plus 0 and 1 plus 0, so I'll get log of 1 by 1, which is log of 1. Log of 1 is 0, so this whole thing goes for a 6. Means it becomes 0. Sorry, I shouldn't say it goes for a 6. I don't need to write that. This becomes 0. So answer is log of s plus 6 by log of s plus 5. So that's what it is, as you can see here on your screen. But what I want to emphasize here is, see, your third semester B is over at this step, very first step. Laplace of somebody by t is integral of Laplace of the numerator. That's all, over. After that, this is PUC integration. This is second PUC integration. This is definition of log. This is evaluation of limits, which you did in first PUC. So this is all PUC problem. You see, about 80% of the problem is PUC problem. It's very easy actually if you know what you have done in your PUC. If you don't know, then you are in trouble. Is that okay? Is that clear? See, the third semester B part is here, this formula. Laplace of ft by t is integral of Laplace of ft. That's all. After this, how to evaluate this? Okay, this is also there. Laplace of e power minus 5t is also what we learned in this semester. It is 1 by s plus 5. And similarly 1 by s plus 6. They are the easy part. The difficult parts seem to be what you have not learned in your PUC and your first year BE. So please, this is just to illustrate that you must learn what you must understand what you have learned before. Otherwise, you will be in trouble. Then otherwise it starts looking very horrendous. It's quite scary to see. If I didn't know anything, if I see these expressions, I'll get scared. So I don't want that to happen to you. So please go through your past studies. So here is another question. Laplace transform of e power minus t sin t by t. More or less you must have been expecting this question because here it is Laplace transform of ft by t, but Laplace transform of ft is easy to find in this because all I have to do is direct application. Laplace of e power minus 5t minus e power minus 6t is Laplace of e power minus 5t minus Laplace of e power minus 6t, both I know. So here somebody wants to make you work a bit harder. So I will use the same philosophy, same formula. Laplace of ft by t is integral of Laplace of e power minus t sin t. But how do I find Laplace of e power minus t sin t? I know I have a formula, shifting formula also I use. So how we do it? Here it is. Here I already, I'm not spending time on that, but I written it down here, but I already explained to you. Laplace of e power minus sin t, sorry, Laplace of e power minus t sin t. How do I find Laplace of sin t is 1 by s square plus 1. Remember, 1 square by s square plus 1 square, Laplace of sin t. Laplace of e power minus t into sin t, replace s by s plus 1, s minus minus 1, which is s plus 1. So this is what Laplace of e power minus t sin t is. Now Laplace of e power minus t sin t by t means you integrate this with respect to s from s equal to s to infinity. Right? That's the last formula which you know, that's the property which we are trying to use of Laplace transform. So then Laplace of e power minus t sin t by t is integral of ds by s plus 1 whole square plus 1 s to infinity. How do I integrate this? Again, your BE problems are all over. Means what you learned in BE is over here. From here onwards, it's only your class 12 integration. How do I integrate 1 by s plus 1 whole square plus 1 with respect to s? That we know it is tan inverse of s plus 1. Put s plus 1 equal to x, you will get dx divided by x square plus 1, which is tan inverse of x. X is s plus 1. So I get tan inverse of s plus 1, s running from 1 to s to infinity. If it is infinity, tan inverse infinity plus 1. Infinity plus 1 is infinity. So tan inverse infinity is pi by 2 and tan inverse other one will remain s. So pi by 2 minus tan inverse s plus 1, which is same as cot inverse of s plus 1. I hope it's clear. Basically, the examiners will want you to go around computing Laplace of this numerator. This is the fundamental idea. When you see a function, if you want to find its Laplace transform, recognize in that function which part can you find Laplace easily, and then try to use one of the properties of Laplace transform. That's the general philosophy in all the problems which I have solved. Observe this general philosophy that will help you to prepare for your examination. Given a horrendous looking function, find in this function one subpart, one part of that function for which it is easy to find Laplace transform. Then try to build up the big function from that small part with some standard additions like this e power minus t or by t, or in the previous case it was something else. You saw all those things before. So this is all basically, as I said, is more of a test about how well you can integrate. That seems to be very important here. If you don't know integration, you are bound to be in trouble. Okay, so now we have what we have done. We have understood what Laplace transform is. We have found, I mean, rather, we have understood the definition of Laplace transform. We have found Laplace transform of some very easy functions. We have seen how Laplace transform behaves with respect with this multiplication by t power n or multiplication by e power at or division by t. These are the things which we have understood. And I think I have shown you sufficiently many problems also based around this. Now I want to talk about Laplace transform of periodic functions. Perhaps many of you are seeing periodic function for the first time. So I will spend a few minutes explaining to you what a periodic function is. This is very important, not just for Laplace transform part. It will keep coming in your Fourier series and Fourier transform part also. So first three modules, this periodicity is important. These functions which are periodic are important. So let us, anyway, we have sufficient time. So let us digress a bit and slowly try to understand what are periodic functions. So definition is easy here. Definition is right here on your screen. A function f is periodic if f of small t plus capital T is f of t for all small t. Capital T is a fixed number. Uh, so what does it mean? Means how do I understand this? I can read the definition, but how do I understand this? Best thing is try to recall what were some periodic functions which you knew well. Two classic examples of periodic functions are sine and cos. They are the best examples and most easily accessible examples. Let us try to understand what does it mean to say they are periodic. We do that by graphing the functions, graphing both sine and cos. I'm sure you have done it 1,000 times or million times. Sine and cos you must have graphed, but I want to bring out the aspect of periodicity in that, which you know well, but I just want to um, make you understand these periodic functions very well. They are the heart of a lot of engineering and application of mathematics in that area. So graph of sine t is what you see on your screen. We know this. This is 0, t equal to 0. This is t equal to pi by 2, where sine pi by 2 is 1. And this is t equal to pi, where sine pi is 0. And similarly, this is t equal to 3 pi by 2. This is t equal to 2 pi. This is equal to t equal to 3 pi, 4 pi. And this side, this is minus 2 pi. Sorry, this is minus pi. This is minus pi by 2. This is minus 3 pi by 2, etc. etc. We know very well that sine function is never bigger than plus 1 or never smaller than minus 1, and we know this is the graph of sine function. We know this well. What I wanted to observe is, you see how suddenly some part of sine graph has become blue from green. Which part has become blue? Sine value of the function between 0 and 2 pi. 0 is here and 2 pi is here. Between them, the value of sine has become blue in this. Why have I made this blue? Observe this. You see 0 to 2 pi, sine looks like this. Only 0 to 2 pi. That means suddenly you must remember to forget what is outside 0 to 2 pi. That means from here, this side I'll forget. From here, this side I'll forget. So I'm left with only the blue line. You see that? Sine function from 0 to 2 pi looks like this. It looks like, I don't know what is this shape. This is sinusoidal curve between 0 and 2 pi. That's all. That's what it is. What I want you to observe is, you see, the same shape continues from 2 pi to 4 pi. You see, whatever is the blue line here, if you cut this blue line and place it on this, then I'll get value of sine from 2 pi to 4 pi. Right? 0 to 2 pi, whatever is the value of sine, same are the values between 2 pi and 4 pi. That is the upshot of this graph. So this blue line, you can repeat it from here to here is also it's the same blue line, just that it was shifted here and now I can put it there. Not just, of course, same thing happens from 4 pi to 6 pi also. The graph is not big enough to accommodate the full thing, but I'm sure you can understand. This shape where my cursor is moving is same as from here to, there's no space, so I'm stopping here. Otherwise, it would have gone like this. So 0 to 2 pi, whatever is the value, 2 pi to 4 pi is the same as the value. 4 pi to 6 pi same is the value. So it's not on the figure, but you can see 6 pi to 8 pi is also same value, 10 pi to 12 pi also is the same value, 1000 pi to 1002 pi also is the same. Not just positive sides, we are not interested, but you should know. Negative side also, it's the same thing. You should know it because for your Fourier series, Fourier transforms, you will need the negative part also. So I'm just helping you to understand whatever comes later. So my minus 2 pi to 0 also, this function looks the same. What does that mean? That means you take any value here between 0 and 2 pi. If I take this, I won't tell you what is this. I'm just showing you by cursor. This value, how far it is from 0. Take the value of sine at that point. The value of sine at this point means I come from here to here. What is the value of sine there? If I travel the same distance from 2 pi and take the value of sine, it will be the same thing. Recall again. Let's go slowly. Let us take pi by 2. So I walk pi by 2 from 0 and I end up here. What is the value of sine pi by 2? 1. Thank you. I'll note it down. Now walk, how much did I walk from 0? I walk pi by 2. Same you walk pi by 2 from 2 pi. So I'll end up with from 2 pi, if I walk 5, if I walk pi by 2, I'll end up at 5 pi by 2. Correct? This 2 pi and this 5 pi by 2. What is the value of sine at 5 pi by 2? Oh, it is same as 1. Whatever is the sine value here is the same. Whatever is the sine value here means I don't know. Some distance I walk from 0. Same distance you walk from 2 pi. The value of sine is the same. That means what? If sine of t plus 2 pi is same as sine of t. Doesn't matter how many 2 pi's you put, how many is later. But if you take sine of 2 pi plus t is same as sine t. It could be any amount. It could be it doesn't have to stop at pi. It could even come 3 pi by 2. And here also I put 2 pi plus 3 pi by 2. So it will come all the way here. So there it is, value is minus 1. You understand what I'm saying? So periodic function means precisely this definition. F of t plus capital T is small ft, where capital T is some number. It depends on the periodicity. That is called periodicity of the function. In this example, in the example of sine t, capital T is 2 pi. That means periodicity is 2 pi. So sine of t plus 2 pi is same as sine t. Similarly, it's the same is true for cos also. How do I know? You can see. Let me try to graph this cos function. So this is a sine function. Cos function is there is a phase lag of pi by 2. You know this. I mean, cos t you must have plotted several times before. Cos 0 is 1. Cos pi by 2 is 0. Cos 3 pi by 2 is minus 1. Cos 2 pi is 0. So, correct? Cos 2 pi is, no, I'm saying something wrong. Cos 0 is, cos 0 is 1, correct? Cos pi by 2 is 0. This is cos pi is minus 1. Cos 3 pi by 2 is 0. And then this is cos 2 pi. Cos 2 pi is 1, correct? This is cos 2 pi plus pi by 2. Each length from here to here is pi by 2. Each vertical line is separated by pi by 2. So this is 1 pi by 2, 2 pi by 2, 3 pi by 2, 4 pi by 2, which is 2 pi. So this is 2 pi, that's correct. So you observe cos function from 0 to 2 pi you observe. How does it look? Here is the graph. You can see that red curve is the cos curve. So only from 0 to 2 pi, it's become whatever color it's called, blue is it, or purple, or I don't know what this color is. So it's certainly different from this red color. So this vessel kind of thing, it's like some sort of vessel or some sort of V, you see, wavy V. It's like this. Now this repeats. See, from here to here, 2 pi to 4 pi, it looks the same. Whatever is between 0 to 2 pi, same thing repeats from 2 pi to 4 pi. Same thing repeats from 4 pi to 6 pi. Same thing repeats from minus 2 pi to 0. Just like what it happened in sine function. Same thing happens here. Here, but of course, values are different. That's okay. But the phenomena is the same. What is the phenomena? You start at any point between 0 and 2 pi. Some point I start here. Here means what? I have walked some distance from 0 to this much. And same distance you walk from 2 pi to from 2 pi in this direction. Whichever point you reach, the cos at that point is same as cos at this point. Correct? So that means what? Cos of t plus 2 pi is cos t. Which means what? Cos is a periodic function with period 2 pi. Like sine. Both sine and cos have same period. They're not same functions, of course. They're shifted. There's a in engineering language we use the term. They have a phase lag of pi by 2. They have a phase lag of 90 degrees. Pi by 2 radians. So this is a periodic function. So I'll just show you everything in one go. So this is a function. So let me recall. Function f is said to be periodic if f of t plus capital T is f of t. There is one small question here. You see f of t plus 4 pi is also same f of t. So what is the period? Is it 2t or 2 pi or 4 pi? Yeah, I know I'm not splitting here. You take the smallest of such periods, because for this, strictly speaking, 2 pi is a period, 4 pi is a period, 6 pi is a period, 10 pi is a period. All of them, all even multiples of pi are periods. But I want to consider the smallest amongst them, other than cheating. And cheating means I'm not being fair. So I don't want to do that. So I will not go into hair splitting definitions of all these things. It's called fundamental period and things like that. Let's not bother about it. So we understand that period is the smallest guy where the function repeats. So that smallest guy where the function repeats, I'm denoting it as capital T. So function f is periodic if f of small t plus capital T is equal to small ft for all t. So as I said, sine and cos are two of the best examples of uh, periodic functions. So why did I do all this? So basically I'm trying to find, I want to find Laplace transform of periodic functions. That's my aim now. So of course, as usual, there's no proof of this formula in your syllabus. So I won't bother writing the proof, but definitely you must know this formula. This is the formula. So so let me read it out for you. Laplace transform of a periodic function f with period capital T. That means ft is a function which is periodic function with period capital T. You can think of it like sine t or cos t. That's very